Matter feels solid, but that solidity is a bit misleading. Everything is arranged with a surprising amount of space. Atoms are mostly gaps, with tiny nuclei held in place by forces that keep their distance rather than by physical contact. The reason a table feels firm or a floor feels stable is not because matter is tightly packed, but because those forces are very good at resisting compression. For almost everything in the universe, that resistance is more than enough. Gravity, however, is persistent. When enough mass gathers in one place, it presses inward steadily, without urgency or drama. Inside large stars, this pressure builds over long stretches of time, quietly pushing against the structure of matter itself. Neutron stars are what form when that pressure goes as far as it possibly can without causing total collapse. They are not defined by explosions or brightness, but by density. Atoms lose their familiar structure, empty space largely disappears, and matter is packed into a state that cannot exist under ordinary conditions. This video takes a calm, careful look at how that happens. It explores how stars support themselves, why that support eventually fails, and what physics looks like when matter is compressed to its practical limit. Along the way, ideas like size, weight, and solidity begin to behave very differently than everyday experience would suggest. Welcome to The Sleepy Scientist. This channel focuses on clear, factual science, told slowly and thoughtfully, to help you unwind while learning something real. If you enjoy this style of exploration, consider liking the video and subscribing to the channel. And if you'd like, let us know where you're watching from in the comments. It's always nice to see where people are listening from. Matter feels solid because it behaves that way in everyday life. A hand placed on a table meets resistance. A foot on the ground does not sink through. Objects hold their shape, keep their edges, and push back when pressed. It is easy to assume that solidity comes from matter being tightly packed, as though everything is filled all the way through. In reality, matter is built very differently. An atom consists of a tiny nucleus surrounded by electrons held in place by electrical attraction. Between those parts is an enormous amount of empty room. If an atom were expanded to the size of a large stadium, its nucleus would be closer to the size of a grain of sand at the center. Almost everything else would be space. The reason objects feel solid has less to do with physical contact and more to do with forces that resist overlap. When atoms are pushed together, their electric fields repel one another long before the nuclei ever come close. This is why most materials are surprisingly hard to compress. Squeezing a solid object means trying to push electron clouds into one another, and those clouds are very good at pushing back. Even enormous pressures applied in laboratories barely change the volume of everyday matter. The structure holds because the forces inside atoms are strong, stable, and well balanced. For nearly all environments in the universe, that balance is enough. Gravity is the one force that does not stop pushing. It does not weaken with patience or lose interest over time. It acts on every bit of mass at once, pulling inward continuously. On small scales, gravity is easy to ignore. The pull between individual atoms is utterly negligible compared to electrical forces. Even on the scale of mountains or planets, gravity shapes large structures without disturbing atomic interiors. Stars are where gravity begins to change the situation. A star forms when a vast cloud of gas gathers under its own weight. As the material falls inward, it heats up, and pressure builds in the core. Eventually, temperatures and densities rise high enough for nuclear fusion to begin. Hydrogen nuclei start combining to form helium, releasing energy in the process. That energy pushes outward, creating a pressure that balances gravity and keeps the star stable. This balance can last for millions or even billions of years. The British astrophysicist Arthur Eddington was among the first to describe stars as systems held in a delicate equilibrium. Gravity pulls inward, energy from fusion pushes outward. As long as the two remain matched, the star holds its shape. Nothing dramatic is required. The star simply exists, quietly converting mass into light. But fusion is not permanent. Stars rely on fuel, and fuel can run out. When the reactions in the core slow down, the outward pressure weakens. Gravity does not adjust in response. It keeps pulling with the same steady insistence it always has. The balance shifts, and the star begins to contract. For smaller stars, this contraction stops before anything extreme happens. The inward squeeze raises temperatures again, igniting new fusion reactions or settling the star into a quieter, denser state. Atomic structure remains intact. Empty space between particles is reduced slightly, but not erased. For larger stars, gravity pushes much further. As a massive star contracts, pressure and temperature rise to levels where new types of fusion become possible. Heavier elements form in stages, each providing energy for a time, but each stage burns faster than the last. Eventually, the core fills with material that can no longer release energy through fusion. At that point, the outward pressure drops sharply. Gravity takes over. What happens next is not sudden in the sense of an explosion, but it is decisive. The core begins to collapse under its own weight. The material is compressed faster than fusion can respond. Electrons are forced closer and closer together, and the resistance that normally keeps atoms spacious begins to falter. This is where stars differ fundamentally from every other environment. On Earth, even the strongest materials fail long before atomic structure is threatened. In stars, gravity operates on such a large scale that it can overwhelm the forces that usually keep matter open and airy. The mass involved is simply too great. The inward pull does not act on individual atoms one at a time, but on the entire core all at once. The American physicist Subrahmanyan Chandrasekhar showed that there is a critical mass beyond which electron-based resistance cannot hold up a collapsing star. Below that threshold, electrons can provide enough pressure to halt collapse. Above it, they cannot. Gravity wins, not because it becomes stronger, but because there is more mass pulling inward than the structure of matter can support. As collapse continues, electrons are squeezed into protons, forming neutrons. This process fundamentally changes the nature of the material. Atoms, as familiar structures, cease to exist. The empty space that once dominated matter is dramatically reduced. What remains is far denser than anything found in ordinary experience. It is important to notice how calm this process is in physical terms. There is no intention, no catastrophe in the emotional sense. Gravity does exactly what it always does. Matter responds according to the laws that govern it. The outcome is unusual only because the conditions are unusual. Neutron stars emerge from this process as natural endpoints, not cosmic accidents. They represent a state where matter has been compressed almost as far as known physics allows without collapsing further. Their existence tells a clear story. Empty space, which dominates the structure of atoms, is not guaranteed. Under sufficient pressure, it can be squeezed away. The familiar architecture of matter can be dismantled and rebuilt into something far denser and stranger, while still obeying the same underlying rules. Observations from organizations such as NASA and major ground-based observatories confirm these ideas indirectly. Neutron stars are detected through their gravity, their radiation, and their remarkable stability. Their masses and sizes match what theory predicts when gravity is allowed to compress matter to extreme limits. Seen this way, neutron stars are not exotic curiosities. They are demonstrations. They show what happens when gravity is given enough material and enough time. They reveal that solidity is not an absolute property, but a condition that depends on balance. Remove that balance, and even space itself can begin to disappear. Understanding this changes how everything else fits together. It reframes stars not as glowing objects in the sky, but as long experiments in pressure and structure. It reframes matter not as fixed and rigid, but as adaptable, capable of rearranging itself under the right conditions. And it sets the foundation for everything that follows, because once space begins to run out, the universe starts behaving in ways that are calm, precise, and far removed from everyday intuition. A star does not hold itself together by chance. It survives because two opposing influences remain in careful balance for an extraordinarily long time. On one side is gravity. Every particle in a star pulls on every other particle, drawing the entire mass inward. Gravity does not switch off, slow down, or tire. From the moment a star begins to form, gravity is always trying to compress it into a smaller and denser shape. On the other side is pressure generated from deep within the star's core. That pressure comes from nuclear fusion. In the center of a star, temperatures are high enough for atomic nuclei to move at immense speeds. When they collide, they can overcome their natural electrical repulsion and fuse together. In stars like the Sun, hydrogen nuclei combine to form helium. This process releases energy, not because matter is being destroyed, but because the fused nucleus is slightly lighter than the sum of its parts. The missing mass is converted into energy, exactly as predicted by Einstein's description of mass and energy being interchangeable. That energy has consequences. It heats the surrounding material and produces an outward pressure that pushes against gravity. The star does not expand endlessly, because gravity is still pulling inward. It does not collapse because fusion is pushing back. The result is a steady state where inward and outward forces are matched closely enough for the star to remain stable. This balance is known as stellar equilibrium, and it is one of the quiet achievements of astrophysics that it can persist for millions or even billions of years. The British astrophysicist Arthur Eddington was one of the first to describe stars in these terms. In the early 20th century, long before nuclear fusion was fully understood, he realized that stars must be powered by a process occurring deep inside their cores, providing the pressure needed to counteract gravity. He described stars not as burning objects in the ordinary sense, but as systems delicately balanced between collapse and expansion. Eddington understood that if this balance were ever lost, the star's structure would change dramatically. What makes this balance so reliable is that fusion responds naturally to changes in pressure. If gravity compresses the core slightly, temperatures rise. Higher temperatures increase the rate of fusion, which produces more energy and more outward pressure. That pressure pushes back, slowing the contraction. If the core expands slightly, temperatures fall, fusion slows, pressure decreases, and gravity regains the upper hand. The system corrects itself. It is a remarkably stable arrangement, and it explains why stars can shine steadily for such long periods without dramatic fluctuations. However, this stability depends entirely on fuel. Fusion works because there are light nuclei available to combine. Hydrogen is abundant in young stars, and it burns slowly and efficiently. Over time, hydrogen in the core is converted into helium. Eventually, the hydrogen supply becomes depleted. When that happens, fusion slows, not because something has gone wrong, but because there is simply less fuel to work with. This is an important distinction. Stars do not fail, they progress. When hydrogen fusion declines, the outward pressure supporting the star weakens. Gravity, which has been waiting patiently all along, begins to compress the core again. This compression raises the temperature, allowing new types of fusion to begin depending on the star's mass. Helium can fuse into heavier elements, releasing energy once more and temporarily restoring balance. For massive stars, this cycle can repeat several times. Each new fuel source burns faster than the last. Hydrogen can last millions of years. Helium burns more quickly. Heavier elements burn faster still. Each stage produces energy, but each stage also moves the star closer to a point where no further fusion is possible. The key idea is that gravity is never defeated. It is delayed. Fusion acts like a temporary support structure, holding gravity at bay for as long as fuel is available. Once the fuel changes or runs out, gravity resumes its inward pull. The star responds by adjusting its structure, seeking a new balance if one is available. This gradual progression is why stellar collapse is not sudden or accidental. It is governed by physics at every step. The timing depends on mass, composition, and internal conditions, but the overall direction is consistent. Pressure declines. Gravity tightens its grip. Observations from space-based instruments operated by NASA and other international observatories confirm this picture across many types of stars. By studying star clusters, astronomers can see stars of different masses at different stages of their lives, all following the same underlying principles. The differences are in scale and timing, not in mechanism. For smaller stars, the story ends gently. Fusion fades. Gravity compresses the core to a point where new pressure sources emerge, and the star settles into a dense but stable remnant. Atomic structure remains intact. An empty space inside matter is largely preserved. For larger stars, gravity pushes further. As fusion stages progress and heavier elements accumulate in the core, the energy return diminishes. Eventually, the core becomes filled with material that cannot release energy through fusion at all. At that point, the outward pressure that has supported the star for most of its life drops sharply. Gravity does not pause to notice. The balance that once held the star steady begins to unravel, not through chaos but through inevitability. The core contracts, density rises, temperatures soar, but there is no new fuel to ignite. The star has reached the limit of what fusion can provide. Seen from this perspective, stellar collapse is not a failure mode. It is the natural consequence of finite fuel and infinite patience on the part of gravity. This understanding reshapes how stars are viewed. They're not static objects glowing forever, nor are they ticking time bombs waiting to explode. They're long-running physical processes, slowly converting mass into energy while gravity waits for its opportunity to resume control. The fact that this balance can last so long is what makes the later stages so striking. When gravity finally begins to dominate, it does so in an environment that has already been shaped and prepared by millions of years of fusion. The outcome depends entirely on how much mass is involved and how much resistance remains. And that is where the story becomes more extreme, because once fusion can no longer help, the question is no longer how brightly a star shines, but how much pressure matter itself can provide before space starts to disappear. Not all stars come to the end of their lives in the same way. The difference is not temperament or environment, but mass. How much material a star begins with determines almost everything about how it lives, how it changes, and how it eventually stops being a star at all. Smaller stars live comparatively quiet lives. They burn fuel slowly, adjust gradually, and fade into stable remnants once fusion can no longer continue. Their deaths are more like long retirements than endings. Atomic structure remains intact, gravity is held in check, and nothing particularly violent is required. Massive stars follow a very different path. From the beginning, their greater mass means stronger gravity. To avoid collapsing under their own weight, they must produce far more energy in their cores. Fusion runs faster. Fuel is consumed more quickly. The balance between gravity and pressure is maintained, but it is harder won and shorter lived. As these stars age, their internal structure becomes layered. Fusion happens in shells rather than in a single central region. Lighter elements fuse on the outside, heavier ones closer to the core. Each layer contributes energy, helping to hold gravity back for a while longer. The star swells, contracts, and rearranges itself as it searches for stability. But there is a limit to how far this can go. Eventually, the core fills with material that cannot provide energy through fusion. The star may still be enormous and luminous on the outside, but at its center, the pressure support that once kept gravity balanced begins to weaken. The core starts to contract under its own weight. This contraction is the turning point. As the core shrinks, its density rises sharply. Temperatures increase, but there is no new fuel to ignite. The energy generated by fusion in surrounding layers can no longer reach the core fast enough to stop the inward collapse. Gravity tightens its grip, accelerating the process. At this stage, the outer parts of the star are still being pushed outward by fusion, while the core is falling inward. The star becomes internally unstable. Pressure builds unevenly. The structure that once held everything together begins to fail. What follows is often described as a supernova, but that word can be misleading. Rather than thinking of a supernova as an explosion driven by violence, it is more accurate to think of it as a release of imbalance. The collapsing core reaches a point where it can no longer compress smoothly. Matter stiffens abruptly as it's forced into an unfamiliar state. The inward motion halts and rebounds. That sudden change sends a powerful shock wave outward through the star. The outer layers, no longer held tightly by gravity, are pushed away. They are not blasted apart for spectacle, but lifted off as the star sheds what it can no longer support. The light produced during this process comes from the energy released as matter rearranges itself, not from combustion in the ordinary sense. In this way, a supernova is less about destruction and more about separation. The star discards its outer material, enriching its surroundings with heavy elements forged during its lifetime. What remains behind is the core, now exposed and compressed to an extreme degree. This remnant is where the future of the star is decided. Mass is the deciding factor here as well. If the core is light enough, the collapse stops when electrons provide sufficient resistance to gravity. The star settles into a dense but stable object, with atoms still recognizable and empty space still present within matter. The story ends quietly. If the core is heavier, electron resistance is not enough. Gravity continues to compress the core past the point where electrons can maintain their separation. Electrons are forced into protons, forming neutrons. The nature of the material changes fundamentally. Atomic structure dissolves. The core becomes something entirely new. This is the threshold that leads to a neutron star. Observations of massive star deaths across nearby galaxies have helped build this picture with increasing confidence. Long-term studies carried out using telescopes operated by the European Southern Observatory have tracked stars before, during, and after these events. By comparing different outcomes, astronomers have been able to link the mass of the original star to the type of remnant it leaves behind. These observations show a clear pattern. The most massive stars live fast, burn fiercely, and end abruptly. Their deaths reshape their surroundings and leave behind some of the densest objects in the universe. The process follows the same physical principles every time. Differences arise from scale, not from chance. What is striking is how little drama the physics itself requires. There's no moment where the laws of nature change or become unpredictable. Gravity pulls inward. Pressure resists for as long as it can. When resistance weakens, gravity advances. Each stage follows logically from the one before it. The formation of a neutron star is therefore not an exception or a cosmic accident. It is one of the expected outcomes when a star begins with enough mass and is allowed to age naturally. The violence often associated with these events is secondary to the calm inevitability of the underlying process. By the time the outer layers have been cast off and the light has faded, the essential transformation has already occurred. Matter in the core has been pushed beyond familiar conditions. Empty space, once abundant inside atoms, has been drastically reduced. The star has crossed a boundary that smaller stars never approach. This moment marks the transition from stellar life to stellar remnant. What remains is compact, stable, and governed by different rules of support than anything encountered before. Gravity has reshaped matter itself, not by forceful intervention, but by steady persistence. Understanding this pathway is essential, because neutron stars do not appear spontaneously. They are born from specific conditions, created by stars that were massive enough to challenge the structure of matter and patient enough to reach the point where resistance finally gives way. The next step is to look more closely at that moment of failure, where the familiar architecture of atoms collapses and a new form of matter takes its place. As gravity tightens its hold on a collapsing stellar core, the familiar ways that matter resists compression begin to change. Heat is no longer the main source of support. Fusion has faded, pressure from energetic motion has weakened, and yet collapse does not immediately run away. Something else steps in to slow it down. That something is not a force in the usual sense. It is a consequence of how electrons are allowed to exist. Electrons are not small solid objects that can be stacked neatly together. They follow strict rules about how close they are permitted to be and how similar their states are allowed to become. When many electrons are crowded into a shrinking volume, those rules matter enormously. As space becomes scarce, electrons are forced into higher and higher energy arrangements, simply because there is nowhere else for them to go. This resistance to being crowded is known as electron degeneracy pressure. It does not depend on temperature. Cooling the material does not weaken it. Heating it does not strengthen it. Electron degeneracy pressure arises purely from crowding. The tighter the space, the more strongly electrons resist being squeezed further, not by pushing outward in the everyday sense, but by refusing to occupy the same conditions as one another. In smaller stellar remnants, this effect is enough to stop collapse entirely. Gravity pulls inward, electrons crowd together, and degeneracy pressure pushes back. The balance holds. Atomic structure remains intact. The object settles into a stable state, dense but familiar. For more massive cores, even this remarkable resistance has limits. The astrophysicist Subrahmanyan Chandrasekhar was the first to show this clearly. As a young scientist working in the early 20th century, He calculated how much mass electron degeneracy pressure could support against gravity. His conclusion was unsettling at the time. Beyond a certain mass, no arrangement of electrons could prevent collapse. This boundary became known as the Chandrasekhar limit. What matters here is not the precise value of that limit, but its meaning. It represents a point where the rules that normally protect atomic structure are no longer sufficient. Gravity does not overpower electrons by brute force. Instead, it compresses the core until electrons are forced into configurations that are no longer physically allowed. When that happens, something fundamental changes. As the core contracts further, electrons are pushed so close to protons that a new process becomes possible. Electrons combine with protons, producing neutrons and releasing neutrinos in the process. This is not a chemical reaction and not a fusion reaction. It is a rearrangement of matter at the subatomic level, driven entirely by pressure and density. The result is a rapid transformation of the core's composition. Atoms as structured systems with nuclei and orbiting electrons cease to exist. The distinction between individual atoms disappears. What remains is a dense collection of neutrons packed together under immense gravity. Empty space, once the dominant feature of matter, is largely erased. It is tempting to describe this moment as violent or catastrophic, but that framing misses what is actually happening. Nothing is being destroyed. Matter is not breaking apart into chaos. Instead, matter is settling into a new configuration that better suits the conditions it is under. The transformation is dramatic only because the conditions are extreme. The physics itself is orderly and precise. In fact, the process is remarkably efficient. As electrons are absorbed into protons, the number of particles decreases, allowing matter to occupy less space. Gravity has effectively found a way to bypass electron resistance, not by crushing it directly, but by changing the rules of what particles are present. Once electrons are no longer available to provide degeneracy pressure, that particular line of defense is gone. For a brief moment, collapse accelerates, but it does not continue unchecked. Neutrons, like electrons, follow their own exclusion rules. They too resist being crowded into identical states. As the core becomes dominated by neutrons, a new form of resistance emerges, known as neutron degeneracy pressure. This marks a clear transition. Before this point, matter behaves in ways that are still loosely connected to everyday experience. Atoms exist, electrons orbit, empty space dominates structure. After this point, those ideas no longer apply. Matter has crossed into a regime where its properties are defined by nuclear physics rather than atomic physics. The transformation from atomic matter to neutron matter is therefore not a collapse into disorder, but a shift into a different level of organization. This idea was deeply counterintuitive when it was first proposed. Even Chandrasekhar himself faced significant resistance from established scientists who were uncomfortable with the implications. The notion that a star could collapse beyond the limits of atomic structure challenged long-held assumptions about stability and matter. Over time, observation and theory aligned. Astronomers began to identify compact stellar remnants, whose masses and sizes could not be explained by electron-supported matter alone. Models incorporating neutron-dominated cores matched what was seen far better. The idea that gravity could compress matter past the atomic stage became not only plausible, but necessary. What is striking is how narrow the transition zone is. There is no gradual fading of atomic identity. Once the Chandrasekhar limit is exceeded, the process unfolds rapidly. Electron support fails. Neutrons form. Matter reorganizes itself decisively. The core settles into a new balance, governed by a different set of constraints. Throughout this process, gravity remains the constant presence. It does not suddenly become stronger, it simply continues doing what it has always done, pulling inward without interruption. The changes arise because matter itself adapts to survive under that pull. This moment defines the birth conditions of a neutron star. It is the point where the familiar architecture of matter gives way, where space within matter becomes scarce enough that particles must change identity to fit. Everything that follows depends on this transformation. Density, gravity, magnetic fields and rotation all build upon the fact that the core is no longer atomic, but something far more compact. Understanding this transition is essential because it explains why neutron stars are not merely smaller versions of ordinary stars. They're built from a different kind of matter altogether, shaped by rules that only become relevant when electrons can no longer resist being crowded. Once that boundary is crossed, the universe reveals a new way for matter to exist, one that is stable, extreme, and quietly astonishing in its precision. Once electrons have been absorbed into protons and atomic structure has dissolved, the collapsing core of a massive star enters an unfamiliar state. The material no longer resembles anything encountered in ordinary matter. Atoms are gone. Empty space has been dramatically reduced. What remains is a tightly packed sea of neutrons, pressed together under gravity that has already overcome every previous form of resistance. And yet collapse does not simply continue without limit. Something new begins to push back. Neutrons, despite being electrically neutral, are not passive particles that can be stacked endlessly. Like electrons, they follow strict rules about how closely they can be packed and how similar their conditions are allowed to be. When neutrons are forced into a shrinking volume, those rules become increasingly important. Space becomes scarce, and neutrons begin to resist being crowded any further. This resistance is known as neutron degeneracy pressure. It is best understood in terms of space rather than force. Imagine trying to fit more and more people into a room where no two are allowed to stand in the same position or move in the same way. At first, rearrangement helps. People shift, rotate, and adjust. But eventually every allowed position is occupied. Adding more people does not simply make things tighter. It becomes impossible without breaking the rules entirely. Neutrons behave in a similar way. As gravity compresses the core, neutrons are forced into higher and higher energy arrangements, because the lower ones are already filled. The tighter the space becomes, the harder it is to find allowed states for additional neutrons. The resistance does not come from particles pushing outward, but from the structure of quantum rules refusing to allow further crowding. This behavior is a consequence of what is known as the Pauli exclusion principle, introduced by Wolfgang Pauli. While the formal details are complex, the core idea is simple enough for spoken language. Certain particles are not allowed to occupy identical states. Once all the available states are filled, further compression becomes increasingly difficult. In a neutron star, nearly every available low-energy state for neutrons is occupied. As gravity continues to squeeze, neutrons are forced into ever more extreme arrangements. The resistance grows rapidly, not because neutrons repel one another in the usual sense, but because the number of permissible configurations shrinks dramatically. Space is no longer something that can be borrowed or rearranged. It has become the limiting factor. This is what ultimately halts the collapse of the core. Neutron degeneracy pressure is far stronger than electron degeneracy pressure for a simple reason. Neutrons are much more massive than electrons. Because of this, they can occupy a much smaller volume before their quantum restrictions become dominant. Electrons begin resisting compression while there is still plenty of room left. Neutrons only begin resisting once matter has been squeezed to extraordinary densities. By the time neutron degeneracy pressure becomes significant, matter is already compressed far beyond anything atoms could tolerate. The result is a stable balance between gravity and neutron resistance. Gravity continues to pull inward, but neutron degeneracy pressure pushes back with equal persistence. The star does not expand. It does not collapse further. It settles into a compact, steady configuration. This balance defines a neutron star. What is remarkable is how different this support mechanism is from anything that came before. Fusion no longer plays a role. Heat is largely irrelevant. Temperature can rise or fall without changing the fundamental structure. What matters now is density and crowding, not motion or energy release. In this state, matter behaves more like a single object than a collection of individual particles. Neutrons are packed so closely that their interactions blur together. The distinction between one particle and the next becomes less meaningful. The interior of a neutron star is not a lattice or a layered structure in the familiar sense. It is a continuous, compressed medium governed by nuclear physics rather than chemistry. This is why neutron stars are sometimes described as giant atomic nuclei. While the comparison is not exact, it captures the idea that the star is held together by the same principles that govern matter inside the nucleus of an atom, scaled up to astronomical size. The strength of neutron degeneracy pressure also explains why neutron stars can support such enormous masses within such small volumes. Gravity is intense, but neutron resistance is equally uncompromising. The two remain locked in balance, neither yielding easily. This balance is not infinite, but it is robust. For a wide range of masses, neutron degeneracy pressure provides enough support to prevent further collapse. This star remains compact, dense, and stable for immense spans of time. Changes still occur, but they are slow and subtle, governed by cooling, rotation, and gradual adjustments rather than dramatic structural shifts. The existence of this balance is supported by observations across many wavelengths. Measurements of neutron star masses and sizes, inferred through orbital motion and radiation patterns, match what theory predicts when neutron degeneracy pressure is included. Without it, these objects simply could not exist in their observed form. What is especially striking is how little room for error there is. Neutron stars occupy a narrow band of physical possibility. If the core had been slightly less massive, electron resistance would have been enough, and neutrons would never have dominated. If it had been slightly more massive, even neutron resistance would fail, and collapse would continue toward an even more extreme outcome. In that sense, neutron stars are balanced on a knife edge. They represent a state where matter has been compressed to near its practical limit without crossing into complete gravitational collapse. Space inside matter has not vanished entirely, but it has been reduced to the minimum allowed by known physics. This makes neutron stars uniquely valuable for understanding how matter behaves under extreme conditions. They are not theoretical curiosities. They are real objects observed throughout the galaxy, quietly demonstrating that the rules governing subatomic particles can scale up to shape entire stars. The transition to neutron-dominated matter marks the moment when familiar intuition fully breaks down. Concepts like hardness, solidity, and even shape lose their everyday meaning. What remains is a form of matter supported not by motion or heat, but by the refusal of particles to violate the fundamental rules that govern their existence. This new kind of matter is what allows neutron stars to persist. It explains how they can exist at all, holding themselves together against gravity that has already overwhelmed every previous defense. And once matter is compressed into this state, density reaches levels that stretch imagination even further, because when space has nearly run out, even small changes in volume carry enormous consequences. Density is a word that usually feels manageable. It shows up in school science, in cooking, even in everyday comparisons. A rock is denser than wood. Metal sinks where plastic floats. These ideas work well because the differences involved are modest. The volumes are familiar. The numbers stay within ranges the mind can picture. Neutron stars do not fit into that category. When matter is compressed into neutron-degenerate form, density stops behaving like a useful everyday concept and starts behaving like a boundary. The usual relationship between mass and size breaks down so completely that familiar comparisons become unreliable almost immediately. One of the most common ways to introduce neutron star density is to say that a small amount of their material would weigh as much as a mountain, or a city, or an entire human population. These comparisons are not wrong, but they are incomplete. They give a sense of scale, but they do not explain why scale itself stops working. The deeper issue is not that neutron stars are dense, but that volume loses its meaning. In ordinary matter, adding mass usually means adding space. A larger object is heavier because it contains more atoms arranged over a greater volume. Even very dense materials still follow this rule. Double the mass and the size increases in a way that feels proportional. In a neutron star, this intuition fails. Once matter is supported by neutron degeneracy pressure, compressing it further does not significantly reduce its volume. The neutrons are already packed as tightly as allowed by quantum rules. There is no spare room to give up. Adding mass increases gravity, but it does not easily increase size. Instead, the star becomes more tightly bound, with gravity pulling harder on a structure that can barely respond by shrinking. This is why neutron stars can contain more mass than the Sun, while remaining only a few tens of kilometers across. The volume is not scaling with mass in the way experience would suggest. The star is not hollow, layered loosely, or puffed up by heat. It is compact almost all the way through. In fact, one of the defining features of a neutron star is how evenly its mass is distributed. Unlike ordinary stars which have extended outer layers and relatively low average densities, neutron stars are dense from surface to core. The outer crust is thin compared to the whole. Beneath it, matter quickly reaches extreme densities and remains there. There is no vast, empty interior. The difference between the surface and the center is significant in detail, but not in the way it would be for a gas-filled star. This near uniformity is part of what makes neutron stars so stable. Gravity pulls inward from every direction, and the resistance provided by neutron degeneracy pressure responds everywhere at once. There are no large regions of low density that can collapse independently. The star behaves more like a single object than a layered system. Understanding this required careful observation, because neutron stars cannot be measured directly with rulers or scales. Their sizes and masses must be inferred indirectly through their gravitational influence, their radiation, and their effects on nearby objects. Space-based observatories operated by NASA have played a key role in this process. By observing neutron stars in binary systems, astronomers can measure how fast companion stars orbit them. Those orbital motions reveal the neutron star's mass through gravity alone. Timing measurements from pulsars add further precision, allowing scientists to estimate sizes and densities with remarkable confidence. The results consistently point to the same conclusion. Neutron stars pack extraordinary amounts of mass into extremely small volumes, with average densities that approach those found inside atomic nuclei. At this point, everyday metaphors begin to strain. If a neutron star were scaled down to the size of a marble, it would still outweigh anything the Earth could support structurally. If Earth itself were compressed to neutron star density, it would fit comfortably inside a small room. These comparisons are arresting, but they only hint at the deeper reality. The true strangeness lies in how matter behaves when pushed into this regime. Volume stops being a flexible property. In normal conditions, materials respond to pressure by changing shape, spreading out, or compressing slightly. In neutron stars, matter has already exhausted those options. Neutrons are locked into a dense configuration that resists further rearrangement. The star's size becomes almost fixed, set by the balance between gravity and neutron degeneracy pressure. This is why adding mass to a neutron star does not make it much larger. In some cases, adding mass can actually make the star slightly smaller, because the increased gravity squeezes the existing structure more tightly. This inversion of intuition is one of the clearest signs that familiar concepts no longer apply. It is also why neutron stars sit so close to the boundary of collapse. There's very little room for adjustment. A small change in mass can push the star closer to a threshold where even neutron resistance is no longer sufficient. Density, in this context, is not just a descriptive property. It is a measure of how close the star is to a fundamental limit. Despite this extremity, neutron stars are not chaotic. Their uniform density and compact size give them remarkable structural coherence. They rotate smoothly, they cool predictably. Their behavior can be modeled with a high degree of accuracy, provided the correct physics is applied. This combination of extremity and regularity is one of their most striking features. There is also a quiet lesson here about scale. Human intuition evolved in a world where density varies modestly and volume matters a great deal. Neutron stars exist far outside that domain. Trying to imagine them using everyday experience is like trying to understand ocean pressure by thinking about a glass of water. The comparison is not wrong, but it is incomplete. What matters more is recognizing that neutron stars reveal a different regime of matter, one where space itself becomes a scarce resource. Inside such an object, adding or removing even a small amount of volume would require enormous changes in energy and pressure. The star's compactness is not accidental. It is enforced by the underlying rules governing neutrons and gravity. This makes neutron stars ideal natural laboratories. They show what happens when matter is pushed to densities that cannot be reproduced on Earth, not even in the most powerful accelerators. They allow physicists to test ideas about nuclear interactions, particle behavior, and gravitational balance under conditions that would otherwise remain theoretical. All of this follows directly from the transition described earlier. Once electrons can no longer resist compression and neutrons take over, density stops increasing in familiar ways and starts acting as a limiting condition. This prepares the ground for a closer look at the internal structure of neutron stars, because although their density is nearly uniform, it is not perfectly so. Subtle changes in pressure, composition, and arrangement still occur beneath the surface. To understand how such an object functions as a whole, it is necessary to look inward, layer by layer, and examine how matter organizes itself when space is nearly run out. Once matter has been compressed into neutron-degenerate form, the neutron star that emerges is not a perfectly uniform block. It has structure, but that structure is unlike anything found in ordinary stars or planets. The differences between regions are subtle, driven by pressure and density rather than chemistry, and they exist under conditions that cannot be recreated directly. What scientists describe as layers inside a neutron star are better thought of as gradual transitions rather than sharply separated shells. At the very outside is the crust. This is the thinnest part of the star, but it plays an outsized role in how neutron stars behave. The crust is solid, extraordinarily rigid, and composed of atomic nuclei packed together far more tightly than any normal material. Electrons still exist here, but they are squeezed into a dense, energetic background rather than orbiting individual atoms in the usual way. As gravity pulls inward, nuclei in the crust become increasingly neutron-rich. Protons remain locked inside nuclei, while excess neutrons begin to leak out and form a kind of background sea. The deeper into the crust, the stranger the arrangements become. Nuclei stretch, distort, and merge into elongated shapes as they compete between nuclear attraction and gravitational pressure. These exotic configurations are sometimes informally compared to sheets, rods, or tangled structures, not because they resemble anything familiar, but because geometry becomes an important part of how matter organizes itself under stress. Even here, empty space is minimal. Everything is crowded, constrained, and tightly bound. Below the crust lies the outer core. This is where atomic nuclei finally disappear entirely. Matter transitions into a dense fluid dominated by neutrons, with a smaller number of protons and electrons still present to maintain balance. The particles move collectively, more like a continuous medium than a collection of individual components. Pressure in the outer core is immense, and density changes slowly with depth. Neutron degeneracy pressure provides the primary resistance against gravity, while nuclear forces influence how tightly particles can pack. The matter here may flow in unusual ways, potentially behaving as a superfluid, where resistance to motion drops dramatically. These properties are not inferred lightly. They are based on decades of theoretical work combined with indirect observational constraints. The behavior of pulsars, their cooling rates, and their responses to stress all provide clues about what the outer core must be like. Deeper still lies the inner core, and this is where certainty begins to fade. Conditions in the inner core exceed anything that can be tested directly. Density reaches levels where even the behavior of neutrons may change. Some models suggest that neutrons could break down into more fundamental components. Others suggest that new forms of tightly bound matter might appear. What matters here is not the details of any one proposal, but the fact that multiple possibilities remain consistent with current observations. This uncertainty is not a failure of science. It is a reflection of honesty. Scientists know what the outer layers must be like because their effects are visible. They know the inner core exists because gravity demands it. What they do not yet know is exactly how matter behaves when pushed that far. There are limits to what observation can tell, and neutron stars sit right at those limits. Direct observation is impossible because neutron stars are opaque. No light escapes from their interiors. No signal carries a clear imprint of conditions deep inside. Everything that is known comes from surface behavior and from how the star interacts gravitationally with its surroundings. To bridge this gap, physicists turn to experiments that explore matter under extreme conditions in other ways. Facilities associated with CERN play a role here, not by recreating neutron stars, but by probing the fundamental forces that govern particles at high energies and densities. Experiments involving heavy ion collisions and particle interactions help constrain how nuclear matter behaves when pushed close together. These results feed into models of neutron star interiors, narrowing down what is physically plausible. Even so, there remains a boundary beyond which inference replaces direct knowledge. The crust is relatively well understood. The outer core is constrained by multiple lines of evidence. The inner core remains an open question, bounded by physics but not yet fully mapped. This layered certainty is an important part of the story, because it shows how scientific understanding advances without pretending to completeness. What is known is that gravity dominates every layer. From the rigid crust to the uncertain core, gravity sets the pressure, the density, and the allowable arrangements of matter. It is gravity that enforces the transitions between layers. It is gravity that determines how tightly neutrons must pack. And it is gravity that ensures the star behaves as a single coherent object, rather than a loose assembly of parts. The layers are not stacked like geological strata. They are compressed into one another, held in place by immense inward pull. There is no sharp boundary where one regime ends and another begins. Instead, properties change gradually as pressure increases, with new behaviors emerging when old ones are no longer possible. This is why neutron stars respond as they do to stress. When the crust shifts or cracks, the entire star feels it. When the core cools or adjusts, the surface responds. The layers are distinct in description but inseparable in practice. Everything is connected by gravity and density. There is also a quiet lesson in restraint here. It can be tempting to fill the unknown with speculation, to imagine dramatic exotic states simply because they sound intriguing. But the most reliable approach is to acknowledge what is known, define what is constrained, and leave the rest open without embellishment. Neutron stars already challenge intuition without requiring added mystery. What makes them compelling is not what might be hidden inside, but how much can already be understood despite the barriers to observation. The picture that emerges is one of partial clarity, a solid crust that behaves unlike any solid on Earth, a fluid outer core where neutrons dominate and move collectively, a deep interior where physics remains, under active investigation, guided by theory, experiment, and observation working together. This layered understanding sets the stage for the next step, because once matter is arranged this way, once mass is packed so tightly and distributed so uniformly, gravity itself begins to behave differently. Its effects become stronger, more pervasive, and more noticeable, not just inside the star, but in the space around it. To understand neutron stars fully, it is not enough to know what they're made of. It is necessary to understand how gravity operates when it's given so much mass in so little space, and how that dominance shapes everything that follows. When matter is compressed into the form found inside a neutron star, gravity stops being a subtle background influence and becomes the dominant feature of the environment. The star's mass has not increased compared to what it once was, but that mass is now confined to an extraordinarily small region. Gravity, which depends on both mass and distance, responds accordingly. This is where space-time itself begins to matter. In everyday life, gravity feels like a simple pull downward. Objects fall, orbits curve gently. Time and space appear fixed and reliable. These approximations work because gravity around familiar objects is relatively weak. The distortions it creates are so small they can be ignored without consequence. Neutron stars do not allow that convenience. Their gravity is strong enough that space and time are measurably altered in their vicinity. Paths that would normally be straight become curved. Clocks closer to the star tick more slowly than those farther away. Light, leaving the surface, loses energy as it climbs out of the gravitational well. This behavior is described by the theory of general relativity, developed by Albert Einstein in the early 20th century. At its heart, the idea is simple enough to express without mathematics. Mass tells space-time how to curve, and curved space-time tells matter how to move. Neutron stars curve space-time deeply, Because their mass is packed into such a small volume, the curvature near their surface is extreme. The star does not merely pull on nearby objects, it reshapes the space through which those objects move. This effect becomes noticeable over very short distances, making the gravitational environment around a neutron star unlike that of any ordinary star or planet. One way to appreciate this is by considering surface gravity. If it were possible to stand on a neutron star, which it is not, the gravitational pull at the surface would be immense. A human body would not experience a gentle downward force, but an overwhelming compression. The difference in gravity between head and foot would be so large that the body could not remain intact. This description does not require exaggeration or drama. It follows directly from scale. The star's mass is comparable to that of the Sun, but the distance from its center is tens of thousands of times smaller. Gravity increases rapidly as distance decreases. On a neutron star, there is simply very little distance left to soften the pull. Yet even here, gravity behaves lawfully. There is no sudden spike, no singular behavior. The equations that describe gravity around Earth also describe gravity around a neutron star. The difference lies entirely in magnitude. The same rules, applied to a far more compact object, produce far more dramatic results. Another way to see this is through escape velocity. Escape velocity is the speed an object needs to leave a gravitational field without falling back. On Earth, it is high but manageable. On a neutron star, it becomes a significant fraction of the speed of light. This means that anything leaving the surface must move extraordinarily fast just to avoid being pulled back. Importantly, this does not mean escape is impossible. Neutron stars are not black holes. Light can still leave their surfaces. Particles can escape if they have enough energy. The gravitational pull is immense, but it has not crossed the threshold where space-time closes in on itself completely. This distinction matters because it highlights how close neutron stars are to a fundamental boundary without crossing it. General relativity predicts that as objects become more compact, gravitational effects grow stronger and more extreme. Neutron stars sit very near the edge of this progression. They warp space-time deeply, but not so deeply that escape routes vanish. They are extreme but still accessible to observation. This makes them valuable testing grounds for gravity itself. Signals emitted from neutron stars carry subtle imprints of the space-time they pass through. Light loses energy climbing away from the surface. Time dilation affects the rhythm of pulsars. Orbital motions in binary systems reveal how gravity behaves when space-time curvature is strong but not absolute. Observations of these effects allow scientists to test predictions of general relativity under conditions far beyond those found near Earth. So far, the theory has performed remarkably well. Neutron stars behave exactly as expected when their mass, size, and rotation are taken into account. There's also a quiet elegance to how gravity operates in these objects. Despite the intensity of the gravitational field, neutron stars are stable. They do not tear themselves apart. They do not collapse further unless additional mass is added. The inward pull of gravity is balanced by neutron degeneracy pressure throughout the star, creating a steady configuration where extreme forces coexist peacefully. This balance is delicate, but it is not fragile. Small disturbances do not cause runaway collapse. The star responds by adjusting its structure slightly, redistributing pressure and maintaining equilibrium. Gravity remains dominant, but it is not uncontested. The curvature of space-time around a neutron star also affects motion nearby in subtle ways. Orbits can precess, paths bend, timing signals shift. These effects are measurable, and have been confirmed repeatedly, providing further confidence in the underlying physics. What makes neutron stars especially interesting is how compactness amplifies everything. A small increase in mass produces a noticeable increase in gravitational strength. A small change in radius produces a large change in surface gravity. The system is sensitive, but predictable. It behaves exactly as the equations suggest it should. This sensitivity becomes important when considering how neutron stars evolve. As they cool, spin, or accrete matter from companions, the balance between gravity and internal pressure shifts slightly. These shifts influence rotation rates, magnetic fields, and emission patterns. Gravity remains the backdrop against which all of these changes play out. Understanding gravity at this scale also prepares the ground for understanding motion. When spacetime is so strongly curved, rotation takes on new significance. Angular momentum is conserved, but its effects are magnified. Small initial rotations can become extraordinarily rapid. Stability depends not only on pressure and gravity, but on how the star spins within the curved space-time it creates. Neutron stars therefore represent a turning point in the story. They are objects where gravity is no longer a gentle sculptor, but a dominant architect. They show how familiar laws operate when pushed to extremes, without breaking or changing character. They demonstrate that space-time itself is flexible, responsive, and deeply connected to the matter it contains. By understanding gravity in this context, the next step becomes clearer. Once mass is packed so tightly, and space-time is curved so strongly, rotation and motion begin to behave in ways that are precise, regular, and sometimes astonishingly fast. To see how neutron stars maintain stability while spinning at incredible rates, it is necessary to look at how rotation emerges from collapse and how gravity shapes that motion from the inside out. When a massive star collapses into a neutron star, almost everything about it changes. Its size shrinks dramatically. Its internal structure reorganizes. Gravity tightens its grip. Yet one property survives the transformation almost untouched, carrying through collapse with remarkable fidelity. The property is rotation. Most stars rotate slowly. Even when that rotation feels rapid on human timescales, it is gentle when spread across the vast size of a normal star. The surface moves steadily, the core turns with it, and the whole system carries a certain amount of rotational motion that has been built up over millions of years. When collapse begins, that rotation has nowhere to go. The key idea here is conservation of angular momentum. In simple terms, if an object is rotating and nothing acts to stop it, that rotation must be preserved. When the object becomes smaller, the same amount of rotational motion is forced into a tighter space. The result is an increase in spin speed. This is not an exotic effect. It can be seen every day. When a figure skater pulls their arms inward, they spin faster. The skater does not add energy. They simply reduce their size, and the rotation adjusts accordingly. The same principle applies to stars, though on a vastly larger and more dramatic scale. As a massive star collapses, its radius shrinks from something enormous to something closer to the size of a city. The amount of rotation it began with is conserved. The result is a neutron star that spins extraordinarily fast. This acceleration happens naturally and predictably. There is no special mechanism required. Gravity compresses the star. Rotation responds. Some neutron stars rotate several times each second. Others spin hundreds of times per second. The fastest known examples, called millisecond pulsars, complete a full rotation in a few thousandths of a second. These objects are not spinning on the edge of chaos. They are stable, balanced, and astonishingly precise. Millisecond pulsars often form in binary systems, where a neutron star draws material from a companion. As matter falls onto the neutron star, it transfers angular momentum, gradually spinning the star up over time. The process is slow, controlled, and well understood. It does not produce instability. It produces order. The result is one of the most reliable natural clocks in the universe. The discovery of pulsars dates back to the late 1960s, when radio astronomers detected regular, repeating signals from space. The pulses were so precise that they initially raised eyebrows. Nothing previously observed in astronomy behaved with such regularity. The signals were first identified by Jocelyn Bell Burnell during her graduate research. What she and her colleagues had found was not an artificial signal, but a rotating neutron star emitting beams of radiation that swept past Earth like the light from a lighthouse. Each pulse corresponded to one rotation. This insight transformed neutron stars from theoretical remnants into practical astronomical tools. Their rotation was not just fast, it was stable. In many cases, pulsars keep time more accurately than atomic clocks over long periods. Tiny deviations in their timing can reveal the presence of companion objects, gravitational waves, or changes in the star's internal structure. What makes this possible is the extraordinary rigidity and compactness of neutron stars. Once formed, they do not deform easily. Their mass is locked into a small volume. Their rotation axis remains fixed unless acted upon by an external influence. This makes their spin behavior clean and predictable. Even when neutron stars slow down, they do so gradually. Over time, rotating neutron stars lose energy through radiation and particle emission. As energy leaves the system, the rotation rate decreases slightly. This process can be measured with exquisite precision. Astronomers can track changes in spin rate over years and decades, building a detailed picture of how neutron stars evolve. Occasionally, small irregularities occur. Some neutron stars experience sudden, tiny changes in rotation speed, known as glitches. These events are thought to arise from interactions between the rigid crust and the superfluid interior. Even these disruptions are orderly in their own way. They follow patterns. They reveal information about the star's internal structure. What is striking is how calm all of this is. The collapse that created the neutron star was extreme. Gravity reshaped matter itself, yet the resulting object spins with mechanical regularity. There is no wobble, no unpredictability, no decay into disorder. The system settles into a state where rotation is one of its most stable features. This is a recurring theme in astrophysics. Extreme conditions do not necessarily produce chaos. Very often, they produce simplicity. Neutron stars strip away complexity and leave behind systems governed by a small number of dominant principles. Gravity, quantum rules, and conservation laws take center stage. Rotation is one of those laws made visible. Because angular momentum is conserved so faithfully, neutron stars remember the motion of the stars that formed them. The spin seen today carries information about the past, encoded in speed and orientation. By studying that spin, astronomers can infer details about formation, accretion history, and internal dynamics. Millisecond pulsars in particular highlight this continuity. Their rapid rotation is not a relic of collapse alone, but the result of long interaction with companion stars. Over time, matter spirals in, transfers momentum, and gently accelerates the neutron star. The final result is a system of remarkable precision, spinning hundreds of times per second without flying apart. This stability exists because gravity and internal pressure remain balanced even at high rotation rates. The star bulges slightly at the equator, but not enough to compromise its structure. The forces involved adjust smoothly. Once again, the system finds a configuration where competing influences coexist without conflict. There's also a practical outcome of this regularity. Because neutron stars spin so predictably, their signals can be used to probe the universe itself. Variations in pulse arrival times can reveal the motion of Earth, the presence of distant companions, or subtle distortions in space-time. Neutron stars become instruments as well as objects of study. All of this emerges from the same simple principle. When collapse reduces size, rotation speeds up. When rotation speeds up, conservation laws enforce regularity. What might seem like a recipe for instability instead produces some of the most precise natural systems known. This is why neutron stars are so valuable to science. They show how order can emerge from extreme change. They demonstrate that even when matter is compressed to its limits and gravity dominates, fundamental principles still apply cleanly and reliably. And it is this regular rotation that makes neutron stars visible across the galaxy. Without it, many would be silent, dark remnants. With it, they announce their presence rhythmically, offering steady signals that can be measured, compared, and understood. Those signals form the basis of the next step in the story, because once rotation and emission combine, neutron stars become more than compact objects. They become tools for exploring space, time, and gravity itself. Once rapid rotation enters the picture, neutron stars become more than dense remnants. They become sources of rhythm. A pulsar is not a different kind of object from a neutron star. It is a neutron star whose rotation and magnetic environment combine in a way that makes it observable. The pulses that give pulsars their name are not bursts or flashes in the usual sense. They are the steady result of geometry, motion, and precision. The starting point is the neutron star's magnetic field. Neutron stars inherit magnetic fields from the stars that formed them, but those fields are enormously intensified during collapse. As the star shrinks, magnetic field lines are pulled closer together, strengthening the field dramatically. The result is a magnetic environment far more intense than anything experienced on Earth. This magnetic field is not neatly aligned with the star's rotation axis. In most cases, it is tilted. That misalignment is crucial. Charged particles near the neutron star are forced to move along magnetic field lines. As they accelerate, they emit radiation. This radiation is not released evenly in all directions. Instead, it is focused into narrow beams that emerge from regions near the magnetic poles. As the neutron star spins, these beams sweep through space. If one of those beams crosses Earth's line of sight, it is detected as a pulse. Each pulse corresponds to one rotation of the star. The regularity of the signal comes not from the emission turning on and off, but from the steady rotation of a highly stable object. This is why pulsars appear to blink. The lighthouse analogy is often used, and while it is imperfect, it captures the essential idea. The beam is always there. The star is always rotating. The pulse appears only because of alignment and motion. What makes pulsars remarkable is not simply that they pulse, but how consistently they do so. Many pulsars keep time with extraordinary accuracy. Their rotation periods are so stable that small deviations can be measured over years. In some cases, pulsars rival or exceed the long-term stability of the best atomic clocks. This precision arises from the same factors discussed earlier. Neutron stars are compact, rigid, and governed by strong gravity. Their rotation is not easily disturbed. Once established, it persists with minimal drift. Because of this, pulsars are not treated as curiosities. They are treated as tools. Astronomers use pulsars as reference points to measure motion, gravity, and time across the galaxy. By tracking the arrival times of pulses, it is possible to detect tiny changes caused by orbital motion, gravitational influences, or even distortions in space-time itself. Timing research carried out at institutions such as the Max Planck Institute for Radio Astronomy has been central to developing these techniques. By monitoring networks of pulsars over long periods, researchers can compare pulse timings with extraordinary sensitivity. Small irregularities become sources of information rather than noise. One application of this precision is the study of binary systems. When a pulsar orbits another object, its motion causes subtle shifts in pulse arrival times. By analyzing those shifts, astronomers can determine orbital parameters, masses, and distances with impressive accuracy. Pulsars act as clocks carried through space, their ticks revealing the structure of the system they inhabit. Another application lies in testing gravity. Because pulsars operate in strong gravitational fields, they provide opportunities to examine how gravity behaves under extreme conditions. Variations in pulse timing can confirm predictions about orbital decay, time dilation, and space-time curvature. These measurements extend gravitational tests far beyond the environment of the solar system. There is also a broader, quieter use. Pulsars help map the galaxy. Their known positions and predictable signals allow astronomers to probe the interstellar medium. As pulses travel through space, they are affected by gas and plasma along the way. By measuring slight changes in timing and frequency, scientists can learn about the material between stars. All of this depends on the reliability of the signal. Pulsars are valuable precisely because they are boring in the best possible way. They do the same thing over and over again, with only small measurable changes. There is no drama in their behavior. No sudden flares are required. Their usefulness comes from consistency. Even when pulsars slow down, they do so predictably. As energy is lost through radiation, rotation gradually decreases. The change is steady and measurable. This allows astronomers to estimate pulsar ages and track their long-term evolution. In some cases, the slowing is interrupted by tiny jumps, but even these are systematic enough to be studied and understood. The language of clocks is therefore appropriate. A clock does not need to be perfect. It needs to be regular. Pulsars meet that requirement with ease. Their pulses provide a steady beat against which other phenomena can be measured. This regularity also helps explain why pulsars were initially surprising. Nothing else in astronomy had previously shown such mechanical precision. Stars were variable. Galaxies evolved slowly. Supernovae flared unpredictably. Pulsars, by contrast, announced themselves with metronomic consistency. Over time, that consistency became familiar. Pulsars are now woven into the fabric of modern astronomy. They are used in experiments, surveys, and long-term monitoring projects. They are part of the infrastructure of observation, quietly ticking away in the background while other discoveries unfold. Their existence also reinforces a central theme of neutron stars. Extreme conditions do not automatically lead to chaos. In many cases, they produce systems that are simpler and more orderly than their gentler counterparts. By stripping away complexity, collapse leaves behind objects governed by a few dominant rules: rotation, gravity, magnetism. The pulses detected from Earth are the surface expression of those rules working together. Each pulse is a reminder that beneath the complexity of stellar life lies a capacity for regularity and precision that can persist long after fusion has ended. This makes pulsars bridges between theory and observation. They connect the internal physics of neutron stars to measurable signals that travel across space. They allow astronomers to test ideas, refine models, and explore environments that would otherwise remain inaccessible. As useful as pulsars are, their behavior cannot be fully understood without considering the magnetic fields that shape their emission. Those fields guide particles, focus radiation, and ultimately determine how the pulses form and evolve. To understand why pulsars look the way they do, and why some neutron stars pulse while others remain quiet, it is necessary to look more closely at magnetism itself and how it behaves when gravity and density push it to extremes. When a massive star collapses into a neutron star, nearly everything about it is compressed. Matter is squeezed, space is reduced. Rotation accelerates. Magnetic fields are no exception. They are carried inward with the collapsing material and intensified dramatically in the process. Magnetic fields behave in a way that makes this amplification almost unavoidable. As the star shrinks, magnetic field lines are forced closer together. This same amount of magnetic structure is confined to a far smaller volume. The result is a field that becomes vastly stronger without requiring any new source of magnetism. Nothing special needs to be added. Collapse alone is enough. This is why neutron stars possess magnetic fields that far exceed anything encountered elsewhere in the universe. Even an ordinary neutron star has a magnetic field trillions of times stronger than Earth's. Compasses would be meaningless nearby. Atoms would behave differently. Charged particles would be locked into narrow paths, unable to wander freely. For some neutron stars, the amplification goes much further. These objects are known as magnetas. They are not a separate class of star, but an extreme expression of the same physical processes. In magnetas, magnetic fields reach strength so high that they dominate the star's behavior. Gravity still holds the star together, but magnetism becomes the most visible influence on its surroundings. Magnetas are rare, but they are not mysterious in origin. They likely form from stars whose initial magnetic fields were already strong and whose collapse conditions favored extreme amplification. Rotation, internal motion, and the details of collapse all play a role. The result is a neutron star where magnetism rivals gravity in shaping what happens at the surface. The presence of such intense magnetic fields has immediate consequences. Charged particles near the star are forced to move strictly along magnetic field lines. Their motion becomes highly ordered. As they accelerate, they emit radiation across a wide range of wavelengths. This radiation is not gentle. It is shaped and channeled by the magnetic field itself. In magnetas, magnetic stress can build up over time. The crust of a neutron star is rigid but not infinitely flexible. As the magnetic field evolves, it can twist and strain the crust. When that strain becomes too great, the crust adjusts suddenly. These adjustments release energy, producing bursts of high-energy radiation that can be detected across vast distances. These events are not explosions in the traditional sense. They are releases of stored magnetic energy, comparable to sudden shifts rather than violent destruction. The star remains intact. The magnetic field rearranges itself. Energy escapes as radiation. Observations of these processes have been carried out extensively using space-based telescopes sensitive to high-energy light. The Chandra X-ray Observatory has played a significant role in studying neutron stars and magnetas in this regime. By examining X-ray emissions, astronomers can infer magnetic field strength, surface conditions, and energy release mechanisms. What these observations reveal is diversity. Not all neutron stars behave the same way. Some are quiet, emitting steady pulses with modest magnetic fields. Others are magnetically active, releasing energy sporadically as their fields evolve. The underlying structure may be similar, but the balance between gravity, rotation, and magnetism differs. This diversity is important because it shows that neutron stars are not a single outcome with a single behavior. They occupy a range of possibilities shaped by initial conditions and long-term evolution. Magnetic fields also influence how neutron stars interact with their surroundings. Strong fields can strip material from nearby space, shape emission regions, and affect how matter falls onto the star from a companion. In binary systems, magnetism can control where accreted material lands and how energy is released. The field acts as a guide, directing matter and radiation alike. Even outside magnetars, magnetic fields remain central to neutron star behavior. They define where radiation is emitted. They influence how the star spins down over time. They shape the structure of the magnetosphere, the region of space dominated by the star's magnetic influence. What makes neutron star magnetism especially striking is how extreme it becomes without becoming chaotic. Despite the immense field strengths involved, the system remains governed by clear physical principles. The fields evolve according to well-understood laws. Their interactions with matter follow predictable patterns. There is no need to invoke unknown forces or speculative physics to explain what is observed. This is another example of a recurring theme. Extreme conditions do not require exotic explanations. They require familiar laws applied at unfamiliar scales. Magnetars may sound extraordinary, but they are built from the same ingredients as every other neutron star. What sets them apart is not a new mechanism, but the degree to which magnetism dominates the system. These strong fields also act as reservoirs of energy. As magnetic configurations twist and adjust, energy is stored and released. This energy can heat the surface, drive radiation, and produce observable events. Over time, as magnetic fields slowly decay, neutron stars cool and quieten. Activity diminishes, the star settles. This gradual evolution links magnetism directly to energy release. Neutron stars do not shine because they burn fuel. They shine because they rearrange stored energy. That energy can come from rotation, from gravity, or from magnetic fields. In magnetars, magnetism is the dominant contributor. Understanding this helps explain why neutron stars can remain active long after their formation. Even when rotation slows and accretion stops, magnetic energy remains. It can power emissions for thousands of years, gradually diminishing as the field relaxes. The variety of neutron star behavior, from steady pulsars to active magnetars, arises from differences in how these energy reservoirs are balanced. Some stars lose rotational energy steadily and quietly. Others release magnetic energy in bursts. Some do both. The underlying object is the same. The expression differs. This diversity prepares the ground for a deeper look at how neutron stars release energy in more dramatic ways, not as explosions, but as sudden adjustments within an otherwise stable system. Because once energy is stored so densely and fields become so strong, even small rearrangements can produce detectable signals across the galaxy. To understand those releases, it is necessary to look closely at how neutron stars respond to internal stress, how their solid crust behaves under extreme conditions, and how energy finds pathways outward when balance shifts. A neutron star may appear unchanging from a distance, but it is not a frozen object. Beneath its steady rotation and regular signals, slow adjustments are always taking place. The star cools, it spins down. Magnetic fields evolve, and as these gradual changes accumulate, they place stress on one of the most unusual solid structures in the universe. The crust of a neutron star is extraordinarily rigid. It is not solid in the everyday sense of wood or stone, but compared to anything else known, it is remarkably strong. Atomic nuclei are packed tightly into a dense lattice, surrounded by a sea of energetic electrons. Gravity presses everything inward with enormous force, locking the structure in place. Under these conditions, the crust can support stresses far beyond those tolerable by any terrestrial material. That strength, however, does not mean flexibility. As the neutron star evolves, its shape and internal balance change slightly. Rotation slows over time as energy is lost. Magnetic fields twist and relax. The interior cools and contracts by tiny amounts. Each of these processes is slow, but none of them is perfectly smooth. The rigid crust resists these changes. When the star's rotation decreases, its overall shape wants to adjust. A rapidly spinning object bulges slightly at the equator. As spin slows, that bulge diminishes. The interior can respond gradually, but the crust, being solid, cannot flow easily. Stress builds as the crust is forced to hold a shape that is no longer perfectly matched to the star's rotation. Magnetic fields add to this stress. As magnetic structures evolve, they tug on the crust from below. Field lines anchored in the solid surface shift and twist, applying uneven forces. Over long periods, these stresses accumulate, stored quietly in the star's rigid outer layer. Eventually, the crust reaches a limit. At that point, it does not shatter violently or explode. Instead, it adjusts. Sections of the crust shift, crack, or rearrange themselves slightly, allowing the star to settle into a new configuration that better matches its internal conditions. These events are known as starquakes. The name invites comparison with earthquakes, and while the analogy is imperfect, it is useful in one respect. Both involve the release of built-up stress in a solid structure. Both are responses to slow changes rather than sudden causes, and in both cases the adjustment itself produces observable signals. In a neutron star, the energy released during a starquake does not propagate through air or rock. It travels through the star's magnetic field and surrounding space. The sudden change in crust structure can alter how particles move near the surface, briefly changing emission patterns or triggering bursts of radiation. These signals can be detected across large distances. Astronomers observe brief changes in brightness, small shifts in pulse timing, or short-lived increases in high-energy radiation. The events are noticeable, but they are not signs of destruction. The star remains intact. Its overall structure is preserved. The adjustment simply allows the system to continue evolving smoothly. One of the clearest signs of starquakes comes from timing irregularities. Some neutron stars experience sudden, small increases in rotation speed, followed by a return to gradual slowing. These changes are tiny, but measurable. They are thought to occur when the crust adjusts and transfers angular momentum between different internal components. The star responds as a whole, maintaining stability while redistributing motion. What is important here is scale. Even a very small rearrangement in a neutron star involves immense energies by human standards. The star is so compact and so massive that slight shifts correspond to large releases of stored stress. Yet from the star's perspective, these events are modest corrections, not catastrophic failures. This difference in perspective is easy to lose. Descriptions of neutron star activity often focus on how extreme the energies are compared to everyday experience. That comparison is accurate but incomplete. What matters more is that these energies are small relative to the star itself. They represent minor adjustments in a system that is otherwise remarkably stable. Starquakes show that neutron stars are dynamic objects. They respond to internal changes. They adapt to evolving conditions. They do not remain locked in the state they were born into. Over thousands and millions of years, they shift, cool, and rearrange themselves gradually, punctuated by occasional adjustments in their rigid outer layers. This evolution is governed by physics, not chance. The stresses build predictably as rotation slows and magnetic fields evolve. The release occurs when thresholds are reached. The star moves from one stable configuration to another without crossing into instability. There is also an important observational benefit to these events. Starquakes provide glimpses into the internal structure of neutron stars. The way the star responds, the timing of adjustments, and the signals produced all carry information about crust strength, internal coupling, and magnetic field behavior. Each event adds a piece to the broader picture. These observations reinforce a key idea. Neutron stars are not static remnants left behind after stellar death. They are active systems with long-term evolution. Their extreme conditions do not lock them into a single state. Instead, those conditions allow slow processes to play out with remarkable clarity. The combination of rigidity and gradual change creates a distinctive rhythm. Long periods of steady behavior are interrupted by brief adjustments. Stability is maintained, but not through rigidity alone. It is maintained through the ability to adapt when necessary. This perspective matters when considering neutron stars in more complex environments. Isolated neutron stars evolve quietly, responding only to their own internal changes. But many neutron stars exist in systems where external influences play a role. Nearby companions can add mass, transfer momentum, and introduce new sources of stress. In those cases, the processes already described do not disappear. They are joined by new interactions. Understanding starquakes as natural adjustments prepares the ground for examining what happens when neutron stars are no longer alone. When they orbit other stars, exchange material, or spiral toward companions, the balance between rigidity and adaptation is tested in new ways, and it is in those shared systems that neutron stars reveal yet another side of their behavior, shaped not only by internal evolution, but by interaction and exchange. Neutron stars are often imagined as solitary objects, drifting through space long after their parent stars have disappeared. Some do exist in isolation, cooling quietly and spinning down over time. But many neutron stars are not alone. They are members of binary systems, bound to companion stars by gravity and shaped by ongoing interaction. These systems introduce an entirely new dimension to neutron star behavior. In a binary system, two objects orbit a common center of mass. If one of those objects is a neutron star, its intense gravity can have a profound effect on its companion. Over time, material from the companion may begin to drift toward the neutron star, drawn inward by the stronger gravitational pull. This process is known as mass transfer. Mass transfer does not usually happen all at once. It is a gradual exchange, governed by orbital motion, stellar winds, and the shape of the gravitational environment around both stars. If the companion star expands or loses material, some of that matter can cross a gravitational boundary and fall toward the neutron star. The material does not plunge straight down. As it moves inward, it carries angular momentum from the original orbit. This causes the infalling gas to spiral rather than fall directly. The result is an accretion disk, a rotating structure of hot material circling the neutron star before gradually settling onto its surface. Accretion disks are not unique to neutron stars, but around neutron stars they behave in especially revealing ways. The disk heats up as material spirals inward, releasing energy in the form of radiation. This radiation can be detected across multiple wavelengths, from visible light to X-rays. The brightness and variability of this emission provide clues about how fast matter is falling in and how the neutron star responds. What is striking is how controlled this process can be. Although the gravitational forces involved are extreme, accretion is not chaotic. Matter follows predictable paths. Angular momentum is conserved. Energy is released gradually as material moves closer to the neutron star's surface. The disk acts as a buffer, regulating how matter is added to the star. As material finally reaches the neutron star, it transfers more than mass. It also transfers angular momentum. This can cause the neutron star to spin faster over time, a process known as spin-up. Many of the fastest rotating neutron stars observed are found in binary systems, where long periods of accretion have gently accelerated their rotation. This interaction changes both members of the system. The companion star loses material and evolves differently than it would in isolation. The neutron star gains mass and rotational energy, altering its emission and internal balance. The system becomes a coupled pair, each influencing the other's fate. Binary systems also allow neutron stars to reveal their mass with unusual clarity. By observing orbital motion, astronomers can measure how fast the two objects move around one another. These motions depend directly on mass. Precise timing of pulsar signals in binary systems has made it possible to weigh neutron stars with remarkable accuracy, confirming theoretical predictions about their structure and limits. These measurements are not merely technical achievements. They provide essential constraints on how matter behaves at extreme densities. Each accurately measured neutron star mass helps narrow the range of possible internal compositions. Binary systems therefore play a key role in connecting observation to theory. There is another quieter consequence of neutron stars sharing orbits. As two massive objects move through space, they affect the fabric of spacetime itself. According to general relativity, accelerating masses produce ripples in spacetime, known as gravitational waves. These waves carry energy away from the system. In most binary systems, this energy loss is tiny and difficult to detect. But in systems involving neutron stars, especially those in close orbits, the effect becomes measurable over time. The orbit slowly shrinks. The stars spiral closer together, not because of friction or contact, but because energy is being carried away by gravitational waves. The process is gradual, unfolding over millions or billions of years, but it is relentless. The existence of this effect was confirmed observationally decades ago through careful study of binary pulsars. More recently, gravitational waves from compact object systems have been detected directly by instruments on Earth, including those operated by the LIGO Scientific Collaboration. These detections marked a turning point. For the first time, neutron stars were not only observed through light and radio waves, but through the motion of spacetime itself. Binary systems became sources of information carried not by particles or photons, but by gravitational waves traveling across the universe. At this stage, it is not necessary to explore those detections in detail. What matters is the role binary systems play in making them possible. Without close orbits, without gradual and spiral, without mass and motion interacting over long time scales, these signals would not exist. Binary neutron stars are essential laboratories for studying gravity, motion, and energy loss in their most extreme but still observable forms. It is also worth noting how calm this process is. The slow tightening of orbits does not involve sudden changes. It proceeds steadily, governed by equations that match observation with remarkable precision. Even as the stars draw closer, the system remains predictable. Each orbit follows the last with only slight adjustments. This reinforces a theme that has appeared repeatedly. Neutron stars may form in extreme events, but they settle into behavior that is orderly, measurable, and governed by clear physical laws. Even when interacting with companions, they do not become erratic, they become informative. Binary systems also highlight how neutron stars influence their surroundings beyond their own surfaces. Accretion disks glow, companion stars change shape, orbits evolve, space itself responds. The neutron star acts as a focal point, organizing motion and energy flow around it. Over time, these interactions can lead to different outcomes. Some binary systems stabilize, with slow accretion and gradual evolution. Others tighten progressively, drawing the stars closer and closer together. In systems where both objects are neutron stars, the process leads toward an eventual encounter. That encounter is not sudden. It is prepared over immense spans of time by the steady emission of gravitational waves and the unchanging pull of gravity. Understanding neutron stars in binary systems therefore sets the stage for understanding what happens when isolation ends completely. When two compact objects no longer orbit calmly at a distance, but move toward a shared fate. The interactions described here are not side stories. They are central to how neutron stars live, evolve, and sometimes meet one another. They show that neutron stars are not just endpoints of stellar evolution, but participants in long, complex relationships that shape both local environments and the wider universe. And in those rare cases where the orbit tightens all the way, where two neutron stars approach closely enough that separation can no longer be maintained, the universe reveals one of its most informative processes, carrying the story from steady interaction into final convergence. When two neutron stars share an orbit, their story does not end with steady companionship. Over very long spans of time, something subtle but persistent changes the relationship. Energy is carried away through gravitational waves, orbit by orbit, quietly tightening the bond between the two stars. The distance shrinks. The motion speeds up. What was once a wide, stable system becomes a slow inward spiral. This process is known as an inspiral, and it is anything but sudden. For most of its duration, the inspiral is calm and predictable. The neutron stars circle one another millions of times, each orbit nearly identical to the last, with only a slight loss of energy each time around. Nothing dramatic happens from one moment to the next. The system evolves patiently, governed by gravity and motion alone. As the stars draw closer, the inspiral accelerates. The loss of energy becomes more noticeable. Orbital periods shorten. Gravitational waves grow stronger. Still, the behavior remains orderly. The physics does not change character. It simply becomes more intense as separation decreases. Eventually, the two neutron stars reach a point where they can no longer maintain distinct orbits. Their gravitational fields overlap strongly. Tidal forces stretch and deform their outer layers. The stars begin to interact directly, no longer as distant companions but as parts of a single, rapidly changing system. The merger itself unfolds quickly compared to the long inspiral that preceded it, but it is best understood as the final step in a process that has already done most of the work. The collision is not a random crash. It is the inevitable outcome of countless earlier orbits, each one carrying away a small amount of energy. What happens during this final stage depends on mass, rotation, and internal structure. In some cases, the merged object briefly forms an even more massive neutron star, held up by rapid rotation and internal pressure. In others, collapse continues further. What matters here is not the precise outcome, but what the process accomplishes along the way. One of the most important consequences of neutron star mergers is the creation of heavy elements. Under normal stellar conditions, fusion can build elements up to iron. Beyond that point, fusion no longer releases energy. Heavier elements require different conditions, involving extreme densities and rapid neutron capture. Neutron star mergers provide exactly that environment. As the stars merge, neutron-rich material is ejected into space. In this environment, atomic nuclei rapidly absorb neutrons before they can decay. This process builds heavy elements that cannot form inside ordinary stars. Gold, platinum, and many other heavy elements are thought to originate, at least in part, from these events. This idea was proposed well before direct evidence was available. For decades, astrophysicists suspected that neutron star mergers could play a role in enriching the universe with heavy elements. But confirmation was difficult. The events are rare. They occur far away, and until recently they could only be inferred indirectly. That changed with the detection of gravitational waves from merging neutron stars. When instruments on Earth first recorded these signals, they provided direct evidence of inspiraling neutron stars completing their final approach. The wave patterns matched predictions precisely, confirming that the inspiral and merger unfolded as expected. Crucially, these gravitational wave detections were accompanied by observations across the electromagnetic spectrum. Telescopes detected light from the same region of space, arriving shortly after the gravitational waves. The characteristics of that light match predictions for material rich in newly formed heavy elements. The combination of signals painted a coherent picture of both the motion and the aftermath. Observational confirmation involved multiple instruments and collaborations working together. Among them was the Virgo collaboration, which contributed to detecting and analyzing the gravitational wave signals. The agreement between theory, gravitational data, and electromagnetic observations marked a significant milestone. What makes this achievement notable is not the spectacle, but the consistency. The signals behaved exactly as expected. The timing matched predictions. The energy release followed known physical laws. There was no need to revise fundamental theory or invoke unknown mechanisms. The universe did what the equations said it would do. This is a recurring theme in the study of neutron stars. Even at their most extreme, these objects follow familiar rules. The conditions are unusual, but the physics remain steady and reliable. Mergers are dramatic only because of scale, not because they are unpredictable. The material ejected during a merger spreads outward, mixing with surrounding gas and dust. Over time, it becomes part of new star systems. Planets form, chemical diversity increases, elements forged in these brief encounters are incorporated into future generations of stars and worlds. In this way, neutron stars influence the universe far beyond their immediate surroundings. They are not just remnants of stellar death. They are agents of cosmic change, contributing to the chemical richness that makes complex structures possible. Their role is quiet but profound, shaping the composition of galaxies over billions of years. It is also worth noting how much of this story depends on evidence rather than inference alone. Gravitational wave signals provide direct information about motion and mass. Electromagnetic observations reveal composition and energy release. Together, they allow astrophysicists to reconstruct events that would otherwise remain hidden. The merger of neutron stars is therefore not just a theoretical curiosity. It is an observed phenomenon, studied through multiple independent channels. Each detection adds confidence, refines models, and improves understanding of how matter behaves under extreme conditions. Despite the energies involved, the process remains governed by limits. Neutron stars can merge, but they cannot do so indefinitely without consequence. There are boundaries to what matter and pressure can support. After the merger, the resulting object must either find a new balance or continue collapsing. This brings the story naturally toward questions of maximum mass and stability. Neutron star mergers push matter into configurations that approach the ultimate limits allowed by known physics. They test how much mass can be supported by neutron degeneracy pressure and how gravity behaves when that support is strained to its edge. By studying mergers, scientists gain insight not only into how neutron stars shape the universe, but into where the boundaries of neutron star existence lie. In this sense, mergers are not just endpoints. They are experiments conducted by nature itself, compressing matter, releasing energy, and revealing how far familiar laws can be stretched without breaking. The inspiral, the collision, and the aftermath form a continuous narrative. Each stage follows logically from the last. There is no sudden departure from physical law, only an intensification of it. Understanding these events completes the picture of neutron stars as dynamic participants in the cosmos. They form, evolve, interact, and sometimes merge, leaving behind lasting imprints on the universe around them. And as these mergers push matter toward its limits, they raise the next essential question. How much mass can a neutron star truly support before even neutron resistance gives way, and gravity finally closes every remaining option? Neutron stars are remarkably resilient objects, but they are not limitless. No matter how rigid their crusts, how strong their magnetic fields, or how effective neutron degeneracy pressure may be, there is a boundary they cannot cross. Gravity always has the final word. The reason is simple in principle, even if complex in detail. A neutron star is held up by a balance between inward pull and internal resistance. Gravity presses inward relentlessly, while neutron degeneracy pressure and nuclear interactions resist further compression. As long as these influences remain matched, the star is stable. It neither expands nor collapses. It simply exists in a tightly bound equilibrium, adding mass changes that balance. When a neutron star gains material, whether through accretion from a companion or through merger with another neutron star, gravity strengthens. The inward pull increases everywhere at once. The internal resistance must respond by supporting greater pressure over the same limited volume. At first, it can. Neutron degeneracy pressure is extremely powerful. Neutrons resist being crowded with great effectiveness, and the star adjusts by becoming slightly more compact. Density increases, gravity grows stronger, the balance shifts, but it does not immediately fail. However, this adjustment cannot continue indefinitely. There's a point at which adding more mass no longer leads to a new stable configuration. The internal resistance reaches its practical limit. Beyond that point, gravity overwhelms every known mechanism that can hold matter up in neutron degenerate form. This boundary is known as the Tolman-Oppenheimer-Volkoff limit. Rather than a single sharp number, it is best thought of as a range. It represents the maximum mass that a neutron star can support before collapse becomes unavoidable. The exact value depends on details that are still being studied, such as the behavior of matter at extreme densities and the precise nature of nuclear interactions inside the core. The idea itself dates back to work in the late 1930s, when physicists began applying general relativity to the problem of compact stars. Among them was J. Robert Oppenheimer, who explored what happens when gravity is allowed to compress matter without classical limits. His work, alongside that of his collaborators, showed that there must be a maximum mass for neutron-supported stars. What matters here is not the historical detail, but the conclusion. Neutron stars cannot grow without bound. There is no version of neutron matter that can support unlimited mass. The resistance provided by neutrons, powerful though it is, eventually runs out of options. The quantum rules that once held collapse at bay can no longer find permissible configurations. This does not happen suddenly or unpredictably. As a neutron star approaches its maximum mass, its structure becomes increasingly strained. Small increases in mass produce larger increases in gravitational pressure. The star becomes more compact. Internal adjustments become harder to accommodate. Stability margins shrink. Observationally, this means that very massive neutron stars are rare. Astronomers have measured neutron star masses with increasing precision, particularly in binary systems. These measurements cluster within a certain range. They do not extend arbitrarily upward. This pattern is exactly what theory predicts when a maximum mass limit exists. Importantly, there is still uncertainty. The precise value of the Tolman-Oppenheimer-Volkoff limit depends on the equation of state of neutron star matter, a description of how pressure responds to density deep inside the star. Because the inner core cannot be observed directly, this equation is constrained by inference rather than measurement. Different models allow slightly different maximum masses. This uncertainty is not a weakness. It is a reflection of honest boundaries in current knowledge. Scientists know that a limit exists. They know roughly where it lies. What remains open is the fine detail of exactly how matter behaves as that limit is approached. What is clear is what happens beyond it. Once a neutron star exceeds its maximum supported mass, no known form of pressure can halt further collapse. Neutron degeneracy fails. Nuclear forces are overwhelmed. Gravity continues inward without opposition. At that point, the neutron star can no longer exist as a neutron star. The transition is not dramatic in appearance, but it is absolute in outcome. The star crosses a threshold beyond which its previous structure is no longer possible. Matter is forced into a state where even the rules governing neutrons are insufficient to provide support. This is where caution is important. It is tempting to describe this boundary in sensational terms, but the physics does not require that framing. The collapse is not a failure or a catastrophe in the narrative sense. It is the logical continuation of the same processes that have been at work all along. Gravity presses inward. Resistance responds until it cannot. This perspective also helps avoid false certainty. The exact point at which collapse occurs may vary from star to star depending on rotation, temperature, and composition. Rapid rotation can temporarily support slightly more mass by providing additional outward influence. Cooling can change internal conditions. Magnetic fields may play minor roles. These factors complicate the picture without altering the fundamental conclusion. There is still a maximum. Understanding this limit is crucial, because it marks the boundary between two very different kinds of objects. Below it, neutron stars exist as stable, observable remnants governed by known physics. Above it, matter enters a regime where space-time itself plays a dominant role. This is why the maximum mass question is so important. It connects everything discussed so far: formation, collapse, degeneracy pressure, density, gravity, rotation, mergers, and energy release all converge here. The fate of a neutron star depends on how close it comes to this boundary. In binary systems, this question becomes especially relevant. When neutron stars merge, the combined mass may exceed what neutron degeneracy pressure can support. Whether the merged object briefly stabilizes or collapses immediately depends on how close it is to the limit. Observations of merger outcomes therefore provide valuable constraints on where the boundary lies. Each detection adds information. By studying which mergers produce short-lived remnants and which collapse promptly, scientists refine their understanding of neutron star stability. The universe, in effect, conducts experiments that cannot be performed on Earth. The maximum mass question is therefore not abstract. It is grounded in observation, guided by theory, and bounded by uncertainty. It defines where neutron stars end and something else begins. Approaching this boundary carefully matters, because beyond it lies a transition that changes not just the state of matter, but the nature of space-time itself. Understanding where neutron stars can no longer hold themselves up prepares the way for examining what happens when gravity finally removes every remaining support. That next step is not a leap into the unknown, but the continuation of a story that has followed gravity's influence from gentle beginnings to its most decisive expression. As a neutron star approaches its maximum supported mass, it reaches a boundary that is precise in consequence, even if some details remain under study. On one side of that boundary, matter still exists in a stable, supported form. On the other, it does not. This dividing line marks the difference between a neutron star and a black hole. The distinction is physical, not philosophical. A neutron star is an object with a surface. It has a measurable size, a definable radius, and a structure that resists gravity through internal pressure. Neutron degeneracy pressure and nuclear interactions act throughout the star, countering the inward pull of gravity. As long as that balance holds, the star remains a neutron star. A black hole is defined by the absence of such support. When gravity overwhelms every known form of internal resistance, collapse continues without finding a new stable configuration. Matter does not settle into another supported state. Instead, space-time itself becomes the dominant feature. The object that forms no longer has a surface in the ordinary sense. The key difference, then, is not simply density or mass, but support. Neutron stars are held up. Black holes are not. This difference has observable consequences. Neutron stars emit radiation from their surfaces. They can be detected as pulsars, magnetars, or X-ray sources. Their emission varies with rotation, magnetic fields, and surface conditions. Signals can be timed, analyzed, and traced back to specific physical processes occurring on or near the star. Black holes do not emit radiation from a surface, because no such surface exists. Any light or matter that crosses a certain boundary cannot return. That boundary is known as an event horizon, and it is best understood here only as a contrast. It marks the point beyond which escape is no longer possible, not a material surface or physical shell. Neutron stars do not possess such a boundary. Light can leave a neutron star. Particles can escape if they have sufficient energy. Radiation emitted from the surface carries information about the star's properties. This alone makes neutron stars fundamentally different objects, even when their masses approach the upper limit. Another distinction lies in how gravity behaves around them. Both neutron stars and black holes produce strong gravitational fields. Both bend space-time noticeably, but the details differ. Around neutron stars, space-time curvature increases smoothly toward the surface and then ends. There is a final layer of matter resisting collapse. Around black holes, space-time curvature continues inward, past the point where matter can remain static. The geometry of space-time itself enforces inward motion. There is no equilibrium to be found once the horizon is crossed. This difference can be observed indirectly. In binary systems, neutron stars and black holes interact differently with companions. Neutron stars can produce regular pulses, surface emissions, and sudden adjustments such as starquakes. Black holes influence their surroundings only through gravity and through the behavior of material orbiting outside the horizon. Accretion disks around neutron stars behave differently from those around black holes, precisely because neutron stars have surfaces. Infalling material can strike the surface, releasing energy in distinct ways. Timing signatures and radiation patterns reflect this interaction. These differences allow astronomers to distinguish between the two objects even when they appear similar in mass. Neutron stars also respond differently to added mass. As discussed earlier, neutron stars approach a maximum mass gradually. Their internal structure becomes strained, but they remain supported until the limit is crossed. Once that limit is exceeded, collapse proceeds rapidly and completely. There is no intermediate hybrid state where the star is partly neutron star and partly black hole. The transition is sharp. Before the boundary, neutron physics dominates. After it, neutron physics no longer applies as a source of support. The object has crossed from one category to another. It is important to emphasize what is known here. Neutron stars have been observed directly in many forms. Their masses, sizes, rotations, and emissions have been measured with increasing accuracy. Black holes have been identified through their gravitational effects and through radiation emitted by surrounding material. The differences between the two are grounded in observation, not inference alone. What is avoided here is speculation about what happens beyond the boundary. The internal structure of black holes is not required to understand the distinction. The presence or absence of support is enough. Neutron stars exist because matter can still resist gravity. Black holes exist because it cannot. This clarity matters because it prevents confusion. Neutron stars are sometimes described as almost black holes, but that phrasing can be misleading. They are not failed black holes or incomplete ones. They are complete objects in their own right, governed by different physical balances. They represent the last stable form matter can take before gravity removes all remaining options. This makes neutron stars uniquely valuable. They sit at the edge of collapse while remaining observable. They allow scientists to study matter, gravity, and space-time under conditions that approach the limits of known physics without crossing into regimes that are inaccessible to direct measurement. Black holes, by contrast, mark the point where observation becomes indirect by necessity. Information about what lies beyond the horizon cannot reach the outside universe. Neutron stars do not have this limitation. Because of this, neutron stars act as bridges. They connect familiar physics to extreme conditions. They allow theories of gravity and matter to be tested where they are most strained, but not yet hidden behind horizons. They offer insight into where stability ends and inevitability begins. Understanding where neutron stars end is therefore not an exercise in categorization. It is a way of identifying the boundary between supported matter and unsupported collapse. That boundary is sharp in outcome, even if some details remain under refinement. Once crossed, the story of the object changes completely. But until that moment, neutron stars remain distinct, stable, and richly informative systems. Recognizing this boundary prepares the ground for understanding why neutron stars matter so much to science. Not simply because they are extreme, but because they exist precisely at the point where physical law can still be observed, measured, and tested under conditions that push it to its edge. Neutron stars matter to physics because they take familiar laws and place them under conditions that cannot be created anywhere else. They are not interesting simply because they are rare or extreme. They are valuable because they act as natural experiments, running continuously, silently testing ideas about matter, forces and structure at scales far beyond any laboratory. At the heart of this value is nuclear physics. Inside a neutron star, matter is compressed to densities comparable to those found inside atomic nuclei. Neutrons are packed together so tightly that their behavior is governed not by chemistry or atomic structure, but by the strong nuclear force and quantum rules. This places neutron stars squarely in the domain of nuclear physics, but on a scale that nuclear physicists could never reproduce directly. On Earth, experiments can probe nuclei one at a time or collide particles at high energies. These experiments reveal how individual particles behave, how forces act over tiny distances, and how matter responds momentarily under stress. Neutron stars extend that picture. They show what happens when nuclear matter is not fleeting, but sustained, stable, and enormous. This allows scientists to test competing ideas about how particles behave when pushed to their limits. One of the central questions in neutron star physics concerns how pressure responds to density deep inside the star. This relationship, known in physics as the equation of state, determines how stiff or compressible matter is under extreme conditions. Different theoretical models predict different behaviors for neutrons at high density. Some allow matter to compress easily, others resist strongly. Neutron stars help decide between these possibilities. Their masses and sizes are not arbitrary. They're constrained by observation. A neutron star that is too massive for a given theoretical model would collapse if that model were correct. The fact that such stars exist rules out entire classes of equations of state. In this way, neutron stars act as filters, eliminating ideas that cannot support what is observed. This is an unusually direct connection between theory and reality. The constraints do not come from assumptions or simulations alone. They come from real objects whose properties must be explained consistently. Every precisely measured neutron star mass and radius narrows the space of acceptable physics. Rotation adds another layer. Rapidly spinning neutron stars reveal how matter behaves when centrifugal effects interact with extreme gravity. The fact that neutron stars can rotate hundreds of times per second without breaking apart places strong limits on how rigid and cohesive their interiors must be. Again, models that cannot accommodate such rotation are discarded. Magnetic fields add further constraints. In magnetars, the interaction between magnetic fields, crustal rigidity, and particle motion reveals how nuclear matter couples to electromagnetic forces under extraordinary stress. Observations of magnetic activity help refine ideas about how particles arrange themselves and how energy is stored and released. None of this would be possible without observation. Facilities that study neutron stars across the electromagnetic spectrum play a crucial role in translating these ideas into testable science. Radio observations, in particular, are central to this effort. Institutions such as the National Radio Astronomy Observatory support long-term monitoring of pulsars and neutron stars, allowing astronomers to track timing, rotation, and interaction with exceptional precision. These observations connect nuclear physics, astrophysics, and relativity in a single system. Neutron stars do not test one branch of physics in isolation. They test how multiple theories coexist. Nuclear forces operate inside the star. Quantum rules govern particle arrangement. Gravity shapes the entire structure. Electromagnetism controls emission and interaction with the environment. All of these must be consistent with one another. This interdisciplinary demand is one of the reasons neutron stars are so valuable. If a theory works in isolation but fails when combined with others, Neutron stars tend to expose the inconsistency. They are unforgiving in that way. They do not allow convenient separation between domains. Everything happens at once. There is also an important philosophical aspect. Physics seeks to understand not only how things behave under ordinary conditions, but how robust its laws are when stretched. Neutron stars represent a regime where stretching becomes unavoidable. They are not engineered extremes. They are natural outcomes of well-understood processes allowed to run their course. That makes them trustworthy test cases. Unlike hypothetical scenarios, neutron stars exist whether or not they are convenient for theory. The universe has already performed the experiment. The task of science is to explain the result. Neutron stars also contribute to understanding limits. They clarify how far matter can be compressed without collapsing completely. They define boundaries between stable and unstable configurations. They show how conservation laws operate under intense pressure. In doing so, they sharpen understanding of where one physical regime ends and another begins. This is not abstract knowledge. The insights gained from neutron stars feed back into many areas of physics. They inform models of nuclear matter. They guide interpretations of particle experiments. They refine predictions in gravitational theory. Even cosmology benefits, as neutron star mergers contribute to understanding element formation and cosmic evolution. What is striking is how much can be learned from objects that are, in one sense, so simple. A neutron star is mostly neutrons, gravity, and rotation. There is little complexity in composition compared to planets or living systems. Yet that simplicity, combined with extreme conditions, makes neutron stars extraordinarily informative. They strip away distractions. There is no chemistry to obscure behavior, no turbulence from fusion, no atmosphere thick enough to complicate interpretation beyond recognition. What remains is physics laid bare, operating under conditions that force it to reveal its limits. This is why neutron stars continue to attract attention across disciplines. Physicists studying the strong force care about them. Relativists care about them. Astronomers care about them. Even particle physicists find them relevant because they test ideas about matter that no accelerator can reach. The value of neutron stars, then, is not that they are strange. It is that they are precise. They provide clear signals. They follow predictable rules. They evolve slowly enough to be studied carefully. And they exist right at the edge of what physics currently understands. By studying them, science learns not only about neutron stars themselves, but about the strength and limits of its own theories. That is why this topic matters. Not as a curiosity, but as a cornerstone. Neutron stars show how the universe behaves when conditions are pushed to their extremes without becoming inaccessible. They remind us that the laws of physics are not fragile. They hold even when space runs out and gravity dominates. And with that understanding in place, it becomes possible to step back from the details and reflect on what neutron stars ultimately represent, not just as objects in space, but as markers of how far matter, structure, and understanding can go before boundaries are reached. By the time the story reaches this point, the title no longer feels abstract. Where matter runs out of space is no longer a metaphor or a dramatic turn of phrase. It is a literal description of a physical condition that arises naturally when gravity is allowed to work without interruption. Neutron stars exist because matter, under sufficient pressure, can no longer afford to be spacious. In everyday experience, space inside matter is taken for granted. Atoms are loose structures. Forces act across gaps. Compression usually means small adjustments rather than fundamental change. That picture holds across planets, stars, and even most stellar remnants. It only breaks down when gravity gathers enough mass into a small enough volume that the usual architecture of matter cannot be maintained. Neutron stars are where that breakdown becomes unavoidable. They're not exotic detours in cosmic evolution. They're not rare accidents produced by unusual circumstances. They are the expected outcome when massive stars age, exhaust their fuel, and leave gravity with nothing left to push against except matter itself. At that point, matter adapts. Electrons resist crowding until they cannot. Atoms dissolve. Neutrons take over. Space between particles shrinks to the minimum allowed by known physical rules. What remains is a state of matter that is not chaotic, not unstable, and not transitional. It is a conclusion that holds. This is one of the most important ideas to carry forward. Neutron stars are not on their way to becoming something else. They are not incomplete objects waiting to fail. For a wide range of masses and conditions, they are stable endpoints. They can persist for immense spans of time, cooling slowly, spinning steadily, adjusting gently as conditions change. Nothing about their existence requires urgency. The processes that create them unfold over millions of years. The forces that support them are constant. The changes they undergo afterward are measured in small corrections rather than dramatic events. Even the most energetic phenomena associated with neutron stars arise from gradual stress accumulation, followed by brief adjustment, not from instability. Seen in this light, neutron stars are calm objects. They sit quietly at a boundary, not straining against it, but occupying it comfortably. Matter has run out of room, and instead of breaking down further, it has reorganized into a form that fits. This calm inevitability is what makes neutron stars so revealing. They show that extreme outcomes do not require extreme behavior. The universe does not need violence or unpredictability to reach its limits. It needs time, mass, and consistency. Gravity supplies all three. Across the story so far, the same pattern has appeared repeatedly. Gravity presses inward. Matter responds using whatever resistance is available. When one form of resistance fails, another takes its place. Only when all known options are exhausted does collapse continue beyond the neutron star stage. This sequence is orderly. Fusion holds gravity back for a while. Electron crowding takes over when fusion ends. Neutron crowding takes over when electrons can no longer help. Each stage is governed by known principles. Each transition occurs because the previous balance is no longer possible. Nothing here is arbitrary. Neutron stars therefore unify several branches of physics into a single narrative. Nuclear physics explains how matter behaves inside them. Quantum rules determine how particles arrange themselves when space is scarce. Relativity governs how gravity shapes the structure as a whole. Electromagnetism shapes what can be observed from the outside. All of these influences converge at the same point. That convergence is what makes neutron stars so valuable scientifically, but it is also what makes them conceptually satisfying. They show that the universe does not abandon its rules when conditions become extreme. It applies them more completely. There are, of course, limits to what is currently known. The precise behavior of matter at the deepest core of a neutron star remains uncertain. Multiple models are consistent with existing observations. Some details of how particles interact at the highest densities are still being refined. The exact value of the maximum mass is constrained but not pinned down to a single number. These unknowns are not gaps in the story, they are edges. They mark where measurement becomes indirect and inference takes over. They define the frontiers of current understanding rather than its failures. Importantly, they do not undermine the central picture. The existence of neutron stars, their stability, and their role as endpoints of stellar evolution are all well established. What remains uncertain lies within boundaries, not beyond them. This balance between knowledge and uncertainty is part of what neutron stars illustrate so well. They demonstrate how science progresses not by claiming completeness, but by defining where confidence ends and exploration begins. They also offer perspective. From a human viewpoint, neutron stars seem extreme because they compress so much mass into so little space. From a cosmic viewpoint, they're simply one of several stable outcomes available to matter under gravity. They are no more dramatic than planets or ordinary stars. They just occupy a different region of possibility. The title of this story points to a physical truth, but it also carries a quieter implication. Space is not guaranteed. It exists where conditions allow it. Remove the conditions and space recedes. Matter adapts. Structure changes. New balances emerge. Neutron stars are where that process becomes clear. They are places where space inside matter has nearly vanished, not because something went wrong, but because nothing intervened to stop gravity from doing what it always does. They are reminders that solidity, emptiness, and structure are all conditional, shaped by forces that operate patiently over time. By following this story from ordinary matter to neutron degenerate cores, from gentle fusion to final balance, a coherent picture emerges. Neutron stars are not exceptions, they are conclusions. They show how far matter can be pushed while still remaining matter. They show where support ends and inevitability begins without crossing into collapse. They show that the universe has preferred resting points, places where competing influences settle into long-term agreement. Standing at that boundary, neutron stars offer a rare vantage point. They allow observation of matter and gravity at their limits, while remaining accessible to measurement. They reveal how much can be understood when patience replaces spectacle and evidence replaces assumption. With that understanding in place, the narrative naturally slows. What remains is not a new mechanism or a deeper extreme, but a reflection on what has been seen. A recognition that neutron stars are not just dense objects in distant space, but markers of how the universe organizes itself when pushed to its edges. They are where matter truly runs out of space, and from that point, the story does not rush forward. It settles, preparing for a final step back, where the implications of everything explored can be gathered into a single, quiet perspective on limits, balance, and the remarkable consistency of the physical world. There is a tendency, when reaching the edges of understanding, to treat limits as failures, as places where explanation runs out or curiosity is forced to stop. In physics, limits are something else entirely. They are features. They are where the structure of reality becomes clearest. Neutron stars sit at one of those boundaries. They are not remarkable because they are loud or violent, but because they are precise. They show what happens when gravity is allowed to act fully on matter without interruption over immense spans of time. They reveal how familiar laws behave when conditions become extreme, not by breaking those laws, but by following them all the way through. Across this story, the same calm logic repeats. Gravity presses inward. Matter resists using whatever means are available. Fusion delays collapse. Electron crowding holds it back longer. Neutron crowding provides the final support. Each transition follows naturally from the last. Nothing is rushed. Nothing is arbitrary. Neutron stars exist because balance remains possible even when space itself becomes scarce. They are stable not because conditions are gentle, but because competing forces still find equilibrium. In that sense, neutron stars are not exceptions, they are natural conclusions. What makes them feel unfamiliar is scale, not behavior. The same principles that govern falling objects and orbiting planets also govern neutron stars. The difference lies only in degree. Mass is greater, distances are smaller, the consequences are stronger, the logic is unchanged. Not everything about neutron stars is known in perfect detail. The deepest interiors remain described by models rather than direct measurement. The precise behavior of matter at the highest densities is constrained but not fully settled. These uncertainties do not weaken the picture. They define its edges. They mark where knowledge ends and investigation continues. That balance between confidence and uncertainty is part of what neutron stars illustrate so well. They show how far understanding can go without speculation. They show how science progresses by defining boundaries honestly, rather than filling gaps prematurely. Neutron stars are not static relics. They cool, spin, interact, merge, and shape their surroundings over long periods. They contribute to the structure of the universe quietly, without urgency or spectacle. Their influence is steady and persistent. Seen this way, neutron stars offer a grounding perspective. They remind us that the universe is not driven by drama, but by consistency. That even at the edge of collapse, order can remain. And that reaching a limit does not mean something has gone wrong, only that something has finished becoming what it can be. At the boundary where matter runs out of space, there is no need for astonishment. Only patience, balance, and the calm reliability of physical law, continuing exactly as it always has,